Very good afternoon. Welcome to lecture 18. So we'll conclude our discussion in this lecture on the different variants of stochastic gradient descent. Hybrid is something we already discussed, right? What was the idea in the hybrid approach? Can you recall? In hybrid, we resorted to a combination of storing, right? Storing stale gradients and updating only the gradient for some sample point, right? Combination of fresh gradient and all others, all of the gradients as stale. And this fresh gradient was the stochastic one. Right, so that was one variant, but we'll see more today. Okay, so we have discussed hybrid and of course all the accelerated and other versions. We'll do Adagrad and then move towards proximal gradient descent. So recap, that the accelerated version was basically nicely summarized, and this is going to be important. This the summary presentation of the accelerated version, because in fact, let me write on the other side. So this accelerated version is what we'll try and realize in some of our approaches today. So WT plus 1 is WT, and then there was this first component, which is our standard minus alpha t gradient update, but this gradient update itself could be on either the vanilla point, or that is vanilla point is WT, or the momentum or velocity updated WT minus 1. And then there was this other pure momentum term, right? One is momentum within the gradient update, but the other is a pure momentum term WT minus 1. So what we'll do today is go beyond just Nesterov and yeah, we discussed that there are many other variants possible where the gamma t and the beta t themselves could be adapted. Okay, so that's where we left out. How about adapting both these terms, gamma t and beta t, and alpha t? And what's the ground for adapting? That's what took us to, right? Basically, can you look at adapt the learning rate based on gradient information until now, right? Without the right learning rate schedule, conversions can be slow and they can be also very sensitive to the initialization. So that's when we took a slight detour and we talked about the second order methods. The second order method that we kind of discussed is the most basic of all. That was the Newton update rule, right? And I'll skip the motivation, but the idea behind the Newton update was this one. Okay, was that we try and kind of get the step size implicitly through the curvature of the function, which is captured to the Hessian, right? And this turned out to actually result from two possibilities. One is a quadratic approximation to the function at every point. Try and solve it exactly, right? Think of gradient descent as the linear one. So looking at a quadratic version of the curve. And there was also another steepest descent perspective in finding this, right? Finding the direction in which the descent is maximum with the caveat or modulo the assumption that this descent direction should have one norm as per the Hessian matrix. Okay, so there are these two perspectives. We saw this update rule, and we also left off saying that the special cases are when, of course, you have identity matrix, but then there are others where you consider the loss function as a sum of multiple loss functions, decomposability, right? That gives you Gauss-Newton. But more generally, there's the approximation through quasi-Newton algorithms, where we try and approximate the inverse of the Hessian. Right? Why is the Hessian? Inverse itself is what we need. Now we are going to go the other extreme. We're going to consider very simple approximations to the Hessian. While you can certainly go ahead and look at the quasi-Newton LB FGS or BFGS in my notes, right? Those are not, those certainly need to be investigated given all the large language modeling and the large neural network applications. They need to be reinvestigated, obviously. But the spirit of this has also been absorbed, as we'll see in Adam, in Adagrad, and so on. Okay, so with this, we move to the first, which is Adagrad. Adagrad, they try and adapt the learning rate. Now, as I said, Adagrad takes an extreme view. What's the extreme view? Okay, so we'll try and map it to this curve, right? So to this expression. What? Adagrad should expand as adaptive gradient, right? That's most intuitive expansion, and that's how it is. So there's an adaptivity based on the gradient, but as I said, the gradient has to reflect through some second order term. While Newton went all the way to say that, so Newton update was this HT is exactly the Hessian inverse, right? Adagrad says, I'm going to look at the outer product involving the gradients so far. So it is not just, approximating based on the or approximation for the inverse of the Hessian. It's a little bit of the momentum as well. Very subtly, right? It's basically saying take so you remember, right? We're basically talking about t as an index into the time. So look at the gradient so far. Now, question might be, what do you mean by gradient so far? Okay, so This is basically GT, T equals 1, T equals 2, blah, 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 until capital T, right? So is it for all the points? No. The assumption so far is, as far as stochastic is concerned, at time index T, we are going to sample a point at random. Yeah, you can have mini batch variants. So as I said, mini batch is kind of a patch on top of the stochastic. So instead of mixing up too many things, we said mini batch is one perspective, right? Adaptivity, or rather, adaptivity was one perspective, accelerated was one perspective. We can try and combine all of them, right? So here, you're basically saying that ST is a diagonal matrix, right? It could be a full rank matrix. And in fact, in practice, it is. Most likely, it's full rank. But it is a sum of, or rather, obtained through a sum of rank 1 matrices. So multiple rank 1 matrices. G1, G1 transpose is rank 1. G2, G2 transpose is rank 1. Sum of T rank 1 matrices, right? So, but of course, what you have done is, so it's a diagonal matrix of all of these. Okay. So you only taken the diagonal of all of these rank 1 matrices, not all of them. So what does diagonal really represent? Yeah, so summation norm square of all the gradients is what the diagonal will represent. Yes, so you have, and you notice that there is an eta t sitting inside as well. Yeah, of course, this entire, so since it's summation norm square, I'm also taking a square root there. So this in part inside is a summation norm. So remember that there is a significant motivation for taking gradient norms, even from curvature information that we get through strong convexity and also Lipschitz smoothness. Right, all of them were all in terms of gradient norm squares. So I mean, it has good enough motivation. One motivation, as I said, is just the approximation to the Hessian, but the other understanding is curvature through the gradient norm square. Okay.
You're not dividing it by the number of time steps, but you just all in the overall alpha. It's not an average.
This is not an average. Yes, this is basically a sum. Right. True. See that it is also sum for the following reason. I mean, you may want to scale it by the number of points because each GT is based on exactly single point. Okay, so some kind of parity is assumed here between time steps T and the number of points. And typically that's what happens, right? I mean, in most of these large language model training, you at best you iterate through every point once. Yes, so you could consider some kind of normalization, but you'll have to also scale up and you not just scale down, scale up as well. The question was, why is there no division by the number of terms? But point is, if you go back to Newton update, right, the inverse of the grade, it was the inverse of the Hessian. It was the inverse of the Hessian. This is Hessian with respect, complete Hessian, not Hessian based on single point, right? So because you're taking these outer products, let me, and so this might be helpful. So you're taking outer products based on the gradient sampled at each iteration. So that's a rank 1 matrix, right? So now you're basically summing across all those points with the understanding that there is some parity between the T, the number of epochs or iterations, and the number of points. For the time being, let's assume capital T equals n, the number of points. Then there should not be any normalization. There should be no need to rescale, rather. There's no need to rescale. And that's what typically happens when you are doing stochastic. Right? You run through all the examples once, at least, maybe multiple times. But in the case of large language models, you may not even run through all points once. So some rescaling might be in order, but that's not being considered here. Right? So HT is kind of assumed to be positive semi-definite. That's the other, you need it to be positive semi-definite. You're taking the inverse here as well. So you would expect invertibility, right? Because this HT inverse basically is the JJth term is basically the square root of all those gradient squares, right? Or rather, the jth component of the gradient squared. So this, just a second, this is a small t. Okay, just correct this I to be t. Let me just do that correction. I'll forget about it. This is t. Oh. Okay, not I. The same t which is sitting here. So this is a jth component. So you'll assume, I mean, there needs to be some invertibility as well. The other important point is this is also motivated by the curvature coming from the Hessian or the surrogates approximation. So that's where I was alluding to, Lipschitz smoothness, the captured through the gradient square, right? Curvature being upper bounded. No. You are doing stochastic sampling t times, and it's only based on those t samples. Yeah, at each point you are randomly sampling. Right? And this, so all you're doing is taking this sum and then the diagonal elements. Off diagonal elements, so you're setting them to 0. That's what it means to have HTS diag, right? The diag operation is just taking diagonal elements and setting off all the off diagonal elements to 0. That's the operation. The other important point is alpha t. What do you do with alpha t? So, by the way, I've also introduced a gamma t inside. You may say, well, what is happening to gamma t? Oh no, that's an that's an eta t. There was a gamma t, there was a beta t, and alpha t, and now I have also introduced a gamma t here. And then the alpha t is basically set to some base learning rate. There's a very interesting blog. I have pointed you to it, but let me also bring this up here. Where is RMS? By the way, you can go to the table of contents. So setup is written long back in 2016, but still quite relevant. So here's Adagrad. In fact, it comes right after Nestor accelerated gradient and momentum. Pretty much the sequence you are following. Somehow it doesn't list hybrid here. So it's a very nicely written blog, right? What does it do? It adapts the learning rate to the parameters, performing small updates for parameters associated with frequently occurring features. So this is giving a different perspective. It's talking in terms of features. So the gradient is in some sense capturing the rate of change of different features, right? Or the ith component of the gradient is talking about the rate of change of the ith feature. So if you look at this outer product, this outer product is capturing feature-wise interaction. And when you start taking the diagonal, it's basically feature importance square, right? So feature importance is like also reflection of how weighted frequency how good the weighted frequency is. So that's frequently occurring features have smaller updates because of the inverse, right? And larger updates, high learning rates for parameters associated with infrequent features. So this was also motivated for sparse data, text data, for example. Right? I know a lot of large language model advancement is also attributed to this kind of understanding associated with sparsity. So back then, this was the first step towards making HGD very effective for large scale learning. For example, while I talked about text, even to learn cats in YouTube videos, just to deal in the space of images, again, the cat is actually trying to find objects in very high dimensional space. Okay, so I mean, here's the other point. I talked about text. So Adagrad was used to train glow word embeddings, as infrequent words require much larger updates than frequent words. Basically, exactly the inverse of the square of the gradient, right? Okay, so yeah.
So it is somewhat similar. Wouldn't it be similar to that as principle when we do principal component analysis and we have sigma square? So does it correlates or does like
To some extent, yes. So think of this as like the first principal component being captured. Yeah, you can. Yes. So it's like the first principal component being captured. Okay, so this you can go through. Now, I'll talk a little bit more about this. So while we talked about 1 upon square root t, there's a eta sitting there. Obviously, same eta we have. But there's an epsilon also added here for smoothing. So epsilon is a smoothing term that avoids division by 0. So some engineering tricks are also required. We are abstaining from more of the engineering discussions here. So this is a nice block which will also take you through the engineering discussion. Yeah, I think otherwise we'll move on. Yeah, I think this was the first effort to try and eliminate the need for manually tuning the learning rate, adapting it. Okay, so the other problem, of course, is its accumulation of square gradients in the denominator. Now your denominators can actually, I mean, can start becoming so big, the sum will keep growing, right? And as a result, the learning rate will just be dampened, then go to 0. There's no additional knowledge after a point. You're doing vacuous updates. Okay, so a nice perspective on accumulate what it means to accumulate gradients. And this also should remind you of, again, our RMO conditions discussions, right? Sufficient degrees condition. So there are all these perspectives will come out, not necessarily for Adagrad, it will come up for all the other algorithms as well. Okay. So you can see that, some desirables are being brought back. So one question is, can I kind of put all of these under one umbrella? So there's Adagrad, there's Ada Delta, there's Adam. We will not do all of them, RMSProp and so on, right? So can all of them be presented under one umbrella? And that's the effort we are putting here. We already saw an effort to put the accelerated versions, right? Gamma T, beta T, all of them. Now there'll be some slight modifications that will be done. And you can see that evidently here, the board. So the modifications are as follows. I'm going to erase this or make some space rather. So the modifications are largely here, the beta T and the alpha T part. I will have to make some space, but so the new terms that have come up are So there's alpha t into a matrix that is also rotating the gradient, right? It is not just a scalar change, there is also a rotational change, rotational transformation. So this is basically a first order change. Well, ht itself is coming from some second order terms. The other difference is with respect to the velocities. Okay, so the other slight change, unlike Adagrad, is that instead of writing HT in this very, very dirty manner, right? I mean, this is not so clean. You might as well actually bring GTs into some new matrix called G. So that's the other effort which will be done. Instead of having HT defined directly in terms of the gradient outer products, we will have a GT, okay, in terms of the gradient. The GT need not be only this. GT can include, of course, the previous gradients accumulated, but it can have some other additional term as well. So I'm going to erase this part as we move on to an umbrella definition. So what we'll have is that HT is just square root, element wise square root of a matrix GT. And this GT itself will be a function of the outer product, summation, etc. And something more. Okay, we'll see more of that coming. Okay. Is this clear? Now we'll move into the details. Yeah. Sorry? In Newton? Newton's update? Yeah. I'm saying it is doing more. It's trying to get to the Hessian. For that, you need to read a little bit also of the LBFGS methods, right? So the fact that gradients can, I mean, the whole idea of quasi approach is that I should not compute mixed partial derivatives, right? Double derivatives I should not compute. That means I have to do something with the gradients. And we have seen enough motivation for how gradient square is an approximation to the curvature in the case of smoothness, etc. Right? Smoothness was kind of characterized by the the gradient square being upper bounded. Remember. So it's a combination. It's a combination of the current intuitions, LBFGS, and we are saying it is not just that, it is also accumulation. So one perspective of accumulation is, of course, momentum, right? But the other perspective of accumulation is that, like quasi-Newton's method do, I'm also able to do this over different points. Because as I keep stochastic sampling, I will actually be covering more and more points. So there are multiple perspectives converging here. It is not just the quasi-Newton. Quasi-Newton is certainly one strong motivation. Is this clear? So it will be beyond the scope of this lecture. I will have to spend significant time. But I think this motivation should be good enough. Okay, so now we want to get into the different variants of this expression, which is based on what GT turns out to be, and what the relationship is between alpha, gamma, beta, and so on. Okay, there'll also be an eta that might come up for Adagrad that we saw earlier. But at a high level, before I show the large table, the simplest is when GT is the identity matrix, right? So obviously you'll assume you'll get one SGD. SGD is one in the table where you would expect GT to be put it this way. The GT will be identity for SGD. And for all others, GT should be, so SGD. What do you think about Nesterov? Nesterov and momentum, Wozniak or whatever, right? What do you think about this? GT will be what in all these cases? GT should be identity, right? So GT will be identity. Now we'll look at it to Adagrad, which is a RMSProp and Adam. We are not looking at Ada delta, etc., but you will get an idea of all of those also. So in the case of Adagrad, RMSProp, and Adam, obviously a GT won't be identity. What we will do is we will update GT in terms of GT minus 1. And that's the reason we have a GT separate from HT, right? Updating, I mean, there's no additivity, right, between HT and HT, additive relation between HT and HT minus 1. But GT you can, right? So we can write this in terms of some function of GT minus 1 and the current set of gradients squared, right, presented in the form of a diagonal matrix. So you can think of it as D, which is GT transpose, right? DT, sorry, this is DT. Huh? Diagonal. So all of these will be some function of this, right? So obviously I won't have space in the table to fill up all of this. Alpha T, beta T, and gamma T, right? We already know one relation. For Nestor accelerated gradient, what happens between gamma T and beta T? Sorry, equal. Yeah, so that also we can write. Gamma T equals beta T. What do I know about Wozniak? Gamma T. Now we need to fill up. So actually in the table we'll actually have separate rows. Yes, no space on the board to write all of this. Okay. So with this, let's actually present this table. Alpha T, most cases is just a base alpha. The reason alpha T is now set to base alpha is because there is already a curvature term HT. Right? There's no point adapting alpha with T as well as having a multiplicative, right, term which actually captures curvature. So alpha T kind of is now set to Z, set to the constant pretty much everywhere except for the last one, which is Adam. In the case of Adam, actually things are a little more complex. Adam tries to bring together Adagrad and RMSProp. So it might help appreciate better, but not completely, right? So Adagrad, adaptive gradient. And we'll see a little bit of what RMSProp is through this table first. So at Adagrad, we already had some intuition, right, earlier. The difference in Adagrad the first time, as we saw on the blog by Sebastian, is also that Adagrad is the first one which tried an accumulated gradients, and of course it had some problems. Most frequently occurring features led to low update, less frequent with more updates, and so on. But the problem was also that you're accumulating too much, denominator is becoming heavy. Remember, this is what we talked. But this is the first which accumulated. So GT minus 1 plus DT, very obvious. That's the update we saw. Now, what is RMSProp doing? The main difference is that instead of just adding, right, to overcome the issue of accumulated gradients becoming leading to a very large denominator, here a kind of convex combination is being invoked. So that's not really accumulation happening. In fact, the beta 2, which is going to be getting multiplied by GT minus 1, is going to dampen the effect of the previously accumulated gradients. This is raised to t, right? So raised to t is exactly what happened with, I think, with Nestor also, right? Well, I mean, it happened with momentum. So momentum itself, you see, momentum itself, when you have this beta t keep getting multiplied every time, the previously accumulated momentum is going to be dampened. So that's the same spirit. So in the spirit of momentum, so here it was just a plus. Here is a beta 2 times GT. The spirit of momentum. The rest should be all straightforward, right? Beta t, by the way, there's another thing happening. Beta t is set to beta in heavy ball and Nestor accelerated gradient. But Adagrad and RMSProp have no element of momentum at all. So they are, RMSProp has a spirit of momentum in its accumulated gradient update. But as far as these fields are concerned, we have no momentum. Right? That's evident here. In fact, let me make it a little colorful, right? Here you can see all these are zero. At least in Adagrad and RMS, probably have alpha, but the betas and gammas are zeros. Right? Now, Adam has brought, because it has brought in. So why are things changing here in Adam? This is an important question to ask. Why suddenly, instead of beta 2 plus 1 minus beta 2, you have beta 2 divided by 1 minus beta 2 raised to t plus 1 minus beta 2 divided by 1 minus beta 2 raised to t, right? Why is this coming? Well, it's coming because of introducing momentum. Momentum has an effect on the way Adam now is doing this convex combinations. It's still a convex combination. I mean, a kind of, right? Is it convex actually? No, it's not convex, right? Beta 2 upon something plus 1 minus beta 2 upon something, but the denominator and numerator don't add, right?
Denominator
Is raised to t. Okay. So, and it is not just, right, convex combination, because the beta t and alpha t in the case of Adam are also kind of getting dampened. So 1 minus beta 1 divided by 1 minus beta 1 raised to t. So what will happen happen if I set a beta 1 raised to t in the denominator instead of beta 1?
Beta is smaller than 1.
Right.
Smaller. The whole update goes up. So it doesn't die out. Alpha and beta.
Alpha and beta would die out. Right. And so will not the GT minus 1 and GT. Okay. So let's go to rudder.io and we'll directly jump to Adam. In fact, we'll spend more time on Adam in the next slide as well. So I think nicely articulated. Momentum can be seen, whereas momentum can be seen as a ball running down a slope. Adam behaves like a heavy ball with friction. Okay, there's a little bit of friction. So these MT are basically now decaying averages. Well, there was already a decaying average earlier, right? But here, there are two things you're looking at. One is momentum, and the other is the second momentum. First momentum is the mean. So this is the first moment. The second moment, the variance. Think of VT as a variance. Okay? And sometimes it's just also called velocity, right? Here, this point is important. So what are they doing here? So why is there a 1 upon beta 1 raised to t, 1 upon beta 2 t raised to t? So there are some biases. If you didn't have this, right? If you just went with these updates, the authors observed that these get biased towards 0. They start becoming 0. So the idea is to shrink the denominator a bit so that they don't start tending to 0 too soon, right? So the shrinking effect has been reflected in the form of a exponent on the denominator, the term being subtracted in the denominator, which would have ordinarily resulted in the term going to 0, the bias, the bias being introduced to make them into 0. Okay. Okay, I think that's it. That's it. And now this is very cryptic Adam update rule. In this blog, there's an epsilon added everywhere. You see, we haven't done that here, but there, what we have done is, this HT, they've kind of added an epsilon everywhere. I don't know if it's equivalent to adding an epsilon to HT. Wait a second. Square root of VT. It's right. This expression of square root of VT hat plus epsilon is equivalent to adding an epsilon to square root of GT. Just check that. So if you recall, no, it will not be here. No, it won't be here. It won't be here. Sorry. So when you actually consider the ith term of HT inverse, you'll have to add an epsilon to the ith term of HT inverse. That's what this is equivalent to. Square root of E hat T plus epsilon. You recall, even with Adagrad, we showed that the blog had this epsilon term added to the denominator. In the case that the denominator starts going to 0, you want to protect against overflows, numerical overflows. Okay. So Adam is trying to now kind of balance multiple things at once. Right? It's trying to get acceleration. It's trying to bring in the advantage of Adagrad, accumulated gradients, adaptive gradients, adapted based on the gradient square, which is the curvature, but also getting sub-elements of RMSProp, which was basically ensuring that the denominator doesn't start becoming so big that there are no updates at all. But then Adam also, because it's also introducing the accelerated variants, there is a bias that is creeping into making the alphas, the update parameters, these parameters start becoming very, very small. So basically, very soon you actually are discounting all of the history. Now that wasn't such a big problem for RMSProp because RMSProp didn't look at acceleration, right? Only when Adam started looking, I said this convex combination had some elements of acceleration. In the case of Adam, there's a compounding effect. There's a beta 2 sitting out from here. And then there is also the effect of this beta T, right? This beta T. So both of them are going to kill all the previous updates. And therefore, there is a 1 minus beta 1 raised to T, 1 minus beta 2 raised to T in the denominator. So that the cumulative effect of these two, the acceleration and the convex combination coming from RMSProp, together do not kill the previous updates. So trying to overcome or negate or mitigate the bias of killing the previous updates. I hope this was clear to everyone. Very nice story. At least there are more approaches, but still Adam is very attractive. I mean, it has kind of been standing the test of time. So what we'll do next, okay, now since you have clarity like we did for a nested of, we'll try and write down the steps. So I said that there are two things happening here. You are capturing the mean and you're capturing the variance, capturing first order and second order terms. So M will be used to capture the mean, V will be used to capture the variance, exactly like in the blog. Okay. So can you write down the steps of the Adam algorithm, which uses heavy ball momentum, and the steps of similar NADM algorithm? So by the way, Adam has, I forgot to mention, Adam is not using Nestor accelerator gradient. Okay, by the way, the two columns are swapped on the slide. Polyak is heavy ball. So there's no difference between Polyak and heavy ball. Okay. So it's called HB, heavy ball. And I'm sorry. And NAG is called, that NAG is NAG, right? So I've just swapped the order, HB followed by NAG. So Adam is basically using heavy ball. Again, if you note, in heavy ball, you have alpha, beta, right? And gamma is set to 0. So here, as I said, gamma is only going to complicate life. We already had a very detailed discussion on how you do next to accelerated gradient. You have to do a lot of bookkeeping. So Adam has used the simpler of those, right? Which is because there's already a lot of complexity. So gamma is set to 0. So what I've said in the next slide is acceleration has two variants. So like you have Adam, which uses HB, NADM, Nestor accelerated gradient, combined with other features of Adam, give you a NADM, right? Gamma T is not 0 in that case. And in fact, gamma T will be set to beta T in the case of Nestor accelerated gradient, sorry, NADM. Okay, so let's write down the steps now for, you want to try writing down steps? Why don't you try? So if you want, I'll go back to the previous slide. I've kind of recapped here on the slide. SGD was WT minus 1 is WT plus minus alpha times whatever, right? HB was WT minus 1, whatever we wrote the board, right? And NAG. So this might help us write down Adam. Right. So I think what you're saying is the GT minus 1. But the point is, you don't have to preserve all the small GT so far. It's just that GT minus 1 needs to be preserved. But that's all diagonal. The way it is updated is always by adding a diagonal matrix and you initialize it the diagonal matrix. Can you try and write down? Anyone? You able to write? Okay. Yes. In as much detail as possible. There's no gamma t, so it's simpler. With gamma t, it will get more complex. Yeah. Which? Oh, block. Okay. Log. Right. I think can add a. It's not. Yeah. GT is a vector. MTs are also, yeah, moments, first and second order moments. And these are exponential moving averages, correct? Huh? Huh? Yeah, element by square. That's why it's called second order movements, yes. We are not considering cross moments. The vector. Mm-hmm. Here, you're talking about this one? Yeah, this will be based on some norm. No, by the way, theta t plus 1. Theta t plus 1 itself is oh no, theta t plus 1 is a vector, no? You're talking about this one, square root Vt hat. So this is component wise. I think this is component wise. Yeah, I mean, the blog is a little kind of loosely written, so you won't find the exact updates here. I mean, why don't we look at the slides? That should be a better, and the dimensions match there. This was just, I think the dimensions are all perfectly written here, right? So alpha t into ht inverse times the gradient. Hmm? Diagonal matrix, yes. Yeah, this matches. So go by this. That was just to show you the motivation. I mean, blogs are not written with so much of notational rigor. I mean, the spirit is all correct, but yes, exponential moving average is what you should be able to articulate. Okay, anyone? Absolutely, absolutely. But I think writing also gives you clarity. So, anyone wants to suggest? You seem to have written some steps, right?
Like we have at particular time t, we have a previous value of GP minus S. Then we calculate the given particular formula. And then we calculate the group by using
Right. Yes. Right. You sample a point, then compute. So let's assume MT minus 1 is 0. Compute the GT for that step. That is MT. VT likewise, as was rightly pointed out. This is going to involve squares of GTs, element wise. This typically this is the element wise product notation. And I already said that they are first moment and second moment. Second moment, but it's uncentered variance, right? Yeah, and then the reason we have this 1 upon beta, 1 minus beta, 1 raised to t, blah, 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 because since MT and VT are initialized to 0, they are biased towards the 0. They are biased towards 0, right? So this I think I've tried to highlight here. They're biased and start becoming 0 when the decay rates are too small. So what you do is to counter that, you normalize them by 1 minus beta raised to t so that it is not going down so fast. So look at this normalization. What will it make? What will it do? It will make 1 upon 1 minus beta raised to t greater than 1. So when you look at the trajectory of updates, then instead of they becoming diminishingly small, we are trying to bump it up a bit. Because already there is a, there's a moving average with damping effect over the accumulated velocity, right? Accumulated gradients. Overall mean should not die out. Exactly. You want the history to go down, but the current mean should not die out. Yes. Also, please remember, there was a double effect, right? There was a double kind of moving average happening, right? One was through this update in the Adagrad, so this upgrade in RMSProp, beta 2, GT minus 1 plus 1 minus 2 beta, GT. And there was another one that was actually coming up because of, in this case, heavy ball. The momentum term, right? So exactly, right? Now this looks notationally correct, right? I mean, unlike the blog. So this is MT hat is still, so I'm not dividing by MT anywhere. Dividing by VT hat or MT hat. VT hat is still a vector. VT divided by 1 minus beta 2 raised to t, blah, blah, blah. Now this is all correct, right? WT plus 1 is WT minus alpha T times vector, and element wise. Basically, you're kind of rescaling. Element wise, you're dividing by the second order moment square root. So this is what the blog was trying to communicate. So be a little careful. Don't go to jump to block too early. Then you'll get a little confused with your notation. Okay, so this is something you can implement. Straightforward to implement. Any questions?
From alpha, that is velocity. We have added momentum when we are.
So V is not velocity, V is variance, uncentered variance, a second order moment.
We have added, we shifted to Adam stochastic. We added HT inverse to an HT inverse to this thing. So what is it? I knew that it is a norm. How it is helping.
So your question is about HT inverse into HT. This one.
We have current state by calculating the gradient.
So we have added momentum. So there are two things, right? Momentum is about direction. Please remember. Whether it is Nestor accelerated or heavy ball, both are about direction. We were still left with the magnitude. We said we'll first prioritize direction, right? Add a momentum on direction, and then we look at the scalar. So we looked at momentum. Then we are stuck with this problem. How do you find that scalar? All our previous proofs, somewhere we'll had 1 upon square root t, some right, find the worst case lower bound and so on and so forth. We wanted to be more principled now, adapt it, right? So like there was a direction adaptation, we wanted also scalar adaptation. We got inspiration from Newton, right? And then there's a Newton increment lambda square, right? I'm not showing those again so that not to clutter, right? So that became an inspiration. Can we get that direction through curvature? Can we, not direction, sorry, magnitude through curvature? Can the curvature estimate the magnitude? Now, of course, we can't use a Hessian. So we looked at quasi approaches, basically inspiration again. And the inspiration from quasi approaches led to the fact that we can also accumulate gradients. One is notion of accumulating gradients because of course we are decomposing over the function itself is supposed to decompose over points. The fact that we are doing stochastic sampling. The other is there's also accumulation in terms of velocity. I mean, you're basically now doing the same velocity thing within the curvature part. So that's where we get into HT inverse into HT. So it all starts with Adagrad. That's why I showed Adagrad first. Like this was our first foray. And here is where we got into HT inverse, right? This HT inverse into gradient part came from here. And then we said, well, this is fine, but what happens if in addition to this, we also, in addition to the regular gradient update and the adaptation there, if I also want to bring in the momentum part. So momentum part will mean I'll have to bring in a beta t here. But the moment I bring in beta t, there is a compounding effect of the adaptation from WT and WT minus 1. See, there is a WT component, WT minus 1 component here. That's how the multiplication happens here. Sorry? HT inverse into HT minus 1. So did I miss a minus 1 there? There was, okay. I think I missed a minus 1 there. Thanks. On the board I have missed. It's there on the slide. Is that okay? alpha is there, but alpha is still playing a much smaller role, right? So if I give you, right, basically the difference is between grading the entire course based on one assignment versus saying, well, now I distribute the assignment, I think the grading based on 50 assignments, and one of them is the Z alpha. So there is one alpha, but that you're not putting all resources in the same bucket, right? And even with alpha, there are some, I mean, there's a beta also. See, for that matter, there's also beta, which is kind of the decay rate. But we have now simplified the beta should be close enough to 1. So we kind of know in what range I have to choose. Okay. So there are other variants. In the blog, you see all the other variants, right? Adamax, extension of Adam. So Adam uses the square, right? HT was like GT basically had a square. Now Adam says I'll use the max value rather than, so it's basically saying instead of accumulating all the gradients or all the different points, I'll see, well, this is the direction of maximum curvature. So the infinity norm is used instead of square. NADM, I already said, is basically Nesterov instead of heavy ball. Eta delta. So RMSProp. So here basically you're looking at there's a weight differences, right? What think of this as, right? So beta 2 GT minus 1 minus beta 2 GT. So what what Eta delta uses is the kind of root mean square operator on the weight differences as well, in addition to just a summation. So think of it as bringing a little bit of a velocity component as well here. Right? There's yes, WT minus 1. Now it turned out that Adam was not converging even for some convex functions. Okay, there was some bug. Oh, this is right, an embarrassment. So in ICLR 2018, there was a theoretical error in Adam, which prevented the VTs from remaining positive. So the VTs are the terms where I presented in the previous slide. This VT in could actually become negative, right? The second order terms. So look at this definition. VT is beta 2 into VT minus 1 plus 1 minus beta 2 GT into GT. Now it's possible that, sorry, huh? The gradient term can be negative. Well, the GT, in a sense, this can become dominant. It's GT into, it's element-wise product of GTs. Yeah, but also note that these are getting dampened. Yeah, I'm just trying to think where, yeah, this is GT into GT square. Oh, sorry, this is the fixed version. So there was a version of Adam where, so this is the fixed version. This is something you can implement, right? This is a fixed version, but there was it was more of a theoretical error in Adam, and the VTs were not. So it was more of theoretical. Sorry, what we have is correct, but this is a corrected version. But there was an error in the previous version where the VTs were not necessarily guaranteed to be positive. So I think Rudder will give a little bit more detail. Even I'm not able to completely recall what that bug was, but there were many other extensions. So now I'll give a little prelude into what is red bound about, right? So how do you even prove many of these or analyze the convergence of these algorithms? Very, very at a high level. I'll talk about regret bound. Yeah, so I think I mentioned this bug is analysis. They didn't have, so the problem was they didn't have theoretical regret bounds backing their analysis until the VTs were guaranteed to be positive. So the updates have given all correct. It is an issue with respect to showing the regret bounds, the theoretical regret bounds analysis were falling apart when you did not have the VTs guaranteed to be positive. That's all. Right? It was not an empirical issue. Okay. Okay. So now let's look at yeah. Okay. There's also one more last note. Adagrad has been very influential because it really brought up for the first time the adaptivity based on curvature information. But is one technique always better than the other? Still, there's no universal winner. But Adam is certainly one of the best, right? So we'll look at some of the recent takeaways, right? So look at this from ICLR 2015, one of the oldest papers, the performance on MNIST, and you look at basically the training error based on number of iterations of the training data set. And you can clearly see Adam here, right? The one in pink. I'll highlight that here. So if you look at Adam, which has momentum, and SGD Nesterov. SGD Nesterov is the vanilla stochastic gradient descent with Nesterov. So both of them are actually doing the best. So momentum is certainly very important. On the other hand, right after that comes the adaptive, which is the Adagrad, right? Ada delta, all of them come next. Sorry, Adagrad is actually much later. There is this RMSProp and Ada delta, which come next. But momentum seems to be the best performing. So the overall understanding is that the Adagrad was while it was a significant improvement over SGD, so it's certainly better than SGD. The bringing back the momentum has been a game changer, right? So that reason is also put, right? In dense settings, when you're actually reducing the dimension, right, from very high dimensional image to lower dimensional images, we don't have sparsity, right? Adagrad, what was it doing? It was basically in sparse dimensional spaces. It was looking at features which are very commonly occurring. But if it's not the case, you have very dense networks, then Adagrad starts performing poorly because of rapid decay in learning rate. So, and it's basically learning on each coordinate, right? That's what we saw. So acceleration, momentum certainly fixes this issue. That is in the form of Adam. But to some extent, RMSProp and Ada delta, which also try and, so Ada delta, while it sounds like Ada delta, it is still a variant of RMSProp. By taking the convex combination, at least it's avoiding the diminishing nature of the denominator. And the other important takeaway is momentum always improves on the non-momentum variant. And in fact, momentum leapfrogs over just Adagrad. Vanilla Adagrad is not as good as, that's what we see here. Is not nowhere compared to what momentum can offer. In fact, so stochastic gradient descent with Nesterov is better than Adagrad. So Adagrad is breakthrough, but only in the context of momentum adapted methods, not by itself. Okay. Now the thing is, all this is done, but generalization is very important. So it's not just about reduction in training error. So there's been some recent work by Wilson et al. The paper is marginal value of adaptive gradient methods in machine learning. So too much adaptation is also a problem, right? So what do they do? For example, adaptive gradient methods, they create more complex solutions. They are against the grain of regularization, right? So in fact, the examples in this theoretical paper is basically more goes on synthetic examples. But that fact remains. I'm not saying that this has reduced the adaptation of Adam, but it also certainly increased the number of questions being asked. Okay, when will it not perform well? Identifying the weak points of any algorithm is also equally important as you celebrate its effectiveness, right? Yeah, so there's diminishing returns beyond a point, and therefore you'll find some amount of saturation. Now people don't talk so much about, these people. Of course, there's renewed interest often in once in a while in second order methods. So new paradigms exist, but within the same paradigm, too much of adaptation has diminishing returns. Okay, so Wilson, like this paper, I mean the data sets are small, CFA10, but you see is specifically in this data set. Let's look at the analysis, right? So if we look at the SGD, which is in black, and the training error, right? So you see the gap between the pink one, the Adam, and the black one, SGD, right? That's what we're trying to show. You see that the gap has actually increased, wider gap in the test data. You have all these variants, heavy ball has a gap of 7.74. RMSProp has some larger. So, I mean, basically the gap is increased, and that is what is being highlighted here. That the generalization capability may not be the best as you keep on adding more complexity to the adaptation process. This is not to discount the fact that heavy ball methods have been effective. Okay, so yeah, I think there are some other interesting papers. Adam convergence studies, method of stochastic optimization based on Adam, and so on. There are also subgradient methods. So we talked about gradient, but what happens if you do again have hinge loss? Right? What do you do? So you can also consider adaptive subgradient methods. Yeah, and so on. Some of these have never been published. Also, Ada delta I think never got accepted in any venue. People have just put it out in archive and then gets adapted. So I'm going to very quickly run through what this empirical risk minimization framework is. Right? What is the notion of regret? Okay. So this is really extra and optional. I'm not going to cover this as part of the exam, but so the whole idea here is, while we already studied learning as mathematical optimization, but there's also this notion of from a machine learning perspective, which is going beyond just optimization. How well can your approach generalize, right? So while stochastic approaches are thought of, surrogates, right? They are good because they often generalize by not looking at all the points. So stochasticity helps. And the lens for showing how they generalize well is also through empirical risk minimization. Okay, so in fact, Frank Wolf, acceleration, variance reduction, many of these some of them have been studied. Many of these can be studied from this viewpoint of empirical risk minimization. So what do you typically do in machine learning? W star is argument of L plus O, right? L is typically either the 0-1 loss, perceptron loss, hinge loss, and so on, the relaxations. And the O is the regularizer, or O or omega. So yeah, this is just recapping. So gradient, while it depends on all data, if you don't factor in all the data, can it lead to better generalization? So basically, you're trying to tackle optimization, but also show how this faster optimization can also lead to generalization. This is really nice, right? My algorithm performs. I mean, I'm able to get results fast in a way that it generalizes better. Okay, so I mean, how many of you are familiar with pack learning? No. So if you have a large hypothesis class, you want to learn from that hypothesis class, right? Get an H from the hypothesis class H, calligraphic H. You want to minimize this error, right? Which is over or xi yi coming from an IID distribution. So we say that the hypothesis space H is pack learnable for all epsilon and all delta, which are non-trivial, that is greater than 0. An algorithm exists such that once I see m examples, and this m should be order of a polynomial order in the number of in the delta. So delta is basically the lack of probability, right? Epsilon is like the error. So polynomial in delta, polynomial in the error. So think of delta and epsilon as both kind of capturing error in two different dimensions. Delta is error in the probability space, epsilon is in the error space. And polynomial in dimension of the hypothesis space. So if I'm always assured that there's an algorithm which will see polynomial number of examples in delta epsilon and dimension of h, and be able to determine a small h from that hypothesis space with good assurance, with probability 1 minus delta. Right? So the higher the value of delta, lower is my confidence. Right? Higher is the probabilistic error, lower is my confidence. Right? Higher is my epsilon, more is the number of examples I'll require. So more examples based on probability of error, probability of the value of error, and the dimension of h. And I'm guaranteed to find an h, right? With this complexity, such that this error of the final hypothesis is a final h from that hypothesis space is kind of epsilon slackness around the optimal error. This error h star is the optimal error. So has this epsilon slackness around the error. So this is the key thing. The m should be a polynomial in these three terms. So what does this mean? Basically, the moment I say that h is pack learnable, then I can quantify the number of examples I'll require to find a reasonably good, probabilistically good, and empirically good hypothesis. Now, in such a setting, right, if I have an adversarial example, xt, yt, now this adversarial, why do I call it adversarial example? Imagine I had a surprise quiz today, right? So my class becomes an adversarial class because people who didn't attend today are going to suffer. So this is an adversarial example, and imagine the marks are averaged over all these surprise quizzes. So there's a regret for people who didn't attend today. So that's why we use the word adversarial here. There is a regret associated with what you would have the best H star had you seen all the examples, right? Versus what you have over the current set, right? So what is the now in such a pack setting? So pack setting where we have this. So the generalization in pack setting means that you're able to quantify. We'll talk about how much the regret can be only when there is a pack setting. That's why pack setting is important to qualify. But beyond the fact that there is the number of examples is polynomial, let's keep that pack setting aside. Okay. So generalization, we'll just focus on generalization, is measured in terms of how this regret vanishes. Right. So if I had access to the best hypothesis versus a hypothesis just based on HT, right? Based on the points I've seen and regretting based on points I had not seen. Can this gap, this regret gap, can it go to 0 as I see more and more examples? Right? So if I had infinite number of classes and infinite number of quizzes, then possibly people who miss a quiz won't have too much regret, right? The problem is when you have finite number of classes and finite number of quizzes. So that's when regret becomes a challenge. So this is a generalization. Now, specifically for stochastic approaches, like including stochastic gradient descent, and you can see some of the analysis that is done for Adam and all of those. What you try and do, you look at this regret, right? The expected value of this gap, and you characterize an upper bound for that. At the upper bound, our very well known terms, RB by square root T, right? It's so all too familiar to us. So either it is within this framework, then we start talking about order T is order 1 upon epsilon square. Right? Now, what I've done here is I've stitched back everything together with respect to the PAC framework. Okay. So this is all within the PAC framework, which I didn't spell out earlier, right? So I'll be able to learn an algorithm by seeing M, which is polynomial, and the number of in my lack of confidence or probabilistic error, empirical error epsilon, and the dimension H with this upper bound on the error. With under these settings, I'll be able to in expected number of iterations, I can get this epsilon approximation, this epsilon which is in the PAC setting, as T is order 1 upon epsilon square. Right? So this M is also going to be important here. So far M was missing. This M is actually going to come from the PAC setting. T is M times RB square by epsilon square. Actually, this M square is not, sorry, this is M is outside. Order M 1 upon epsilon square. It cannot be M square. Is this clear? So this is just an extra optional reading. What I'll do in the next class is, okay, so I wanted to start this proximal gradient descent, won't have time. I'm going to just present a teaser. That's what we'll continue. But next week, we're going to have project presentation. So I'll continue this the week after that. But just in 1 or 2 minutes, what we are doing next is we are going back to the non-stochastic case. We can bring back stochasticity any point of time, right? We have enough ammunition. What do we do when we have a non-differentiable component in our objective, like hinge loss we've been talking about? One is you say, oh, subgradient descent, I know that, right? And we saw some papers. Can we do better than subgradient descent? And in fact, you can do better than subgradient descent. That's what I want to tell you. And this is an important part. When you either have a non-differentiable component or a component which is just a constraint. I put a constraint that my norm of W should not exceed some threshold. Can I do better? There are very, very nice techniques, right? So that's what brings us to generalized gradient descent. Generalizing subgradient descent for non-differentiable and constraint cases. And we'll go back to our old notation, which is X as variables, not W as variables, right? And the setting here is going to be this. I will stop at this slide. And you should also think a bit, right? If you have a differentiable function F and a non-differentiable function C, okay, what can you do? What is the obvious answer? Right. So an obvious answer is subgradient. Take the subgradient of the whole thing. But a better answer might be find the gradient for F. And now consider the C component. So don't consider C initially. Find a vector which comes close enough to the gradient of F, but which also minimizes C. So think of it as an alternating process, but interestingly, this is the notion of generalized gradient descent, right? So we will do this, right, after the next week.
Differentiable component will minimize C.
Right. Why would I be interested in computing the gradient as some kind of a sentinel? It's like a sentinel, right? Adding it, saying, well, get me C close enough. See, the thing is, C has multiple subgradients. If it is not differentiable, I mean, if it's convex, of course. Now, at least can I get a subgradient which is aligned with the overall objective instead of this subgradient? One motivation for this is, can I get something that's more aligned with the overall objective minimization? As such, we are iterative here. We are not finding closed form solution. Okay. See, other thing is if C is a constraint indicator. If you are within this region, I'm fine. If you're outside this region, my loss is infinity. That's a problem case, right? Now, what can I do? I'll find a gradient for F and I'll project. I'll say, okay, this F is gradient. I will now project within this region. Simple constraint. Let's take the simplest of constraint where I say my W weight should be positive. If my W weight should be positive, what is the point computing subgradient here? See, right? I'll compute the gradient of F and my X1 should be positive. Project. See, this is intuitive. We'll give it a lot of mathematical flavor, right? That entire projection operation, how it results in some very nice convergence properties as well. Is that clear? Okay, thanks. Thanks for your attention. So, anyone of you was going to present next week? No, right? So maybe different groups. But we'll have the class here, and the students will present. But we'll also kind of have the same teams, which I record my class. So I'll attend it remotely, only for next week. Thanks. But all the presentations will be otherwise in the class. And please do participate. I mean, the projects, the seminar presentations are all continuation of this. So we are here to learn. So please do participate. Ask your friends to participate in your peers' presentations. Thank you.